Okay, so today we're going to start on chapter 3. And this is a shorter chapter. There's 6 sections. And so we're going to learn about logarithmic and exponential functions. And that will lead up to making logarithmic and exponential models in chapter 2, or in section 3.6, because all of these sort of lead to the same. And so you'll find each chapter, as you learn some new sort of function, you'll learn how to model it. And so this chapter will be the exponential and logarithmic. Of course, next chapter will be the one you really like, the trigonometric functions. How to model sine, cosine, tangent, cotangent, cosecant, secant. And then pretty much for the rest of the book, it works on those trigonometric functions. So the rest of the pre-calculus is all those trig functions after that.
What trig functions?
Sine, cosine, tangent.
No.
That's pretty much,
Why?
at least for 3 or 4 chapters of that. So this chapter, what we're going to do is, so I've broken into 2 sections. So the first will be 3.1 to 3.3, and so we'll have a quiz on those after those first 3, and then we'll do the last 3, and then a test. So let's talk about exponential and logarithmic functions. What is the definition of an exponential function? The exponential function f with a base a is denoted by f of x equals a to the x. Notice that a has to be positive. We don't use a negative number, so the base is positive. And notice that a does not equal 1. Okay? And the reason for that is what? In this here where we have...
Because then it would just be 4, or it would equal a.
Well, if a was 1, it would be 1. If a is 1, then it would be 1. No matter what you raised 1 to, it's always 1. You multiply 1 times anything, and it's going to stay 1. So your limitations are that a has to be positive, and it can't be 1. But then it can be any real number. Okay? So the first 2 chapters we spent learning about polynomial and rational functions. Those are algebraic functions. And so if you're taking notes, those are important because if you get a question to ask you, those are algebraic functions. In this chapter, we start studying the transcendental functions. So that's what these are. The exponential and logarithmic functions are transcendental. Okay. Well, I don't think it means the same thing in literature. Okay. So, notice that, and again, these should be smooth, continuous curves.
Yeah, no worries.
It's harder to do that when you're drawing on the starboard. So this one, y equals a to the x, increases from left to right. Okay, so your y values continue to get larger as you move, as the x gets larger without bound. And it's the opposite if your exponent is negative. And so you will decrease from left to right as x goes to infinity without bound. And so all of these, though, notice have one point in common, and that's this point 1, 1. And that's because if x is 1, it's just a. Okay? And so, or even if it's a negative exponent, it's a if you raise it to the first power.
Well, 1 to anything is going to be 1. It could be 1 to the 1 million.
So, as you can, so these graphs will transform just like all the others. So, for example, if I had y equals a to the x plus 2, well, this would just be the same graph. I'll lower that a little bit. It would just be up a couple. Just shift it up. Or the same thing, if this was minus 2, it would shift down. Okay? You could have a plus 2 to the, it should be f of x, these functions, not y, but you could have a plus 2, which would give you your horizontal shift to the left, or it could be minus 2, your shift to the right. So these will transform just like all the other functions transformed. And then finally, notice that your stretch and your shrink also work. So if this is f of x equals 2a to the x, well, this just means that it just gets closer to the y-axis there. Yeah, that's our stretch.
A to the x, so that's some number. Oh,
Any number.
wait.
A is just any number.
Oh, okay, never mind.
Okay.
No. Pretend I'm not here.
All right. So, and then of course, if it was 1/2 a to the x, or let's say a to the minus x, so I can do it over here, then it would be, it would just shrink down a little bit away from there. So it's going to do all the normal transformations. So there's nothing new other than this is the exponential function. And so once you know what the exponential function looks like, was that the last? Make sure that was the last page.
What? Yeah.
Okay.
What was E?
And that's okay. That was it for that page. Okay. I left something on for my old.
What is this?
What is what? The natural base E? That's what we're going to go over now.
Oh.
This isn't too bad.
Hey, you know what? Excitement.
So, the number E, it's Euler's number, and so it's his last name, even though it's pronounced Euler, starts with an E, and that's where the E comes from. He was the mathematician that came up with that infinite series, and it's an irrational number, just like pi is. So, the number E will go, it will never terminate, it will never repeat, it will just go on forever. And so I think I calculated out the first 10 or 12, but those will, I should do the ... because those will keep going on forever. Notice it's 2.7182, blah, 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 and it'll keep going out. And so I estimated it, I think, when I did it for this presentation, to 12 places, but it'll go out infinitely number of times. It's irrational. So what is it? Well, it's defined as the series 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 and so forth. They'll just keep on going. So it would be 1 over 1 times 2, 3, 4, 5, and you just keep adding those up. Okay? This number is called the natural base. So the function f of x equals e to the x is called the natural exponential function. So if your base, remember e is just a number. E is just a number. And so we started out by saying an exponential function was f of x equals a, which could be any number to the x. And so you could easily graph this as, pick a number, Kelly, because it doesn't really matter what number you pick. Okay, so that just means that it would go up to 0 through 7. But, you know, it's going to look like that. And this is the exponential function from the previous page, is what it looks like.
So 7 is A?
And what you just picked, yeah. So this would be
Okay.
Wait, 7
f of x equals,
Then what that, no, but then
what?
0 to the 7 is 1, isn't
So 0 to X.
It's the same X. Right. What's your...
But then, like, what
The
happens?
7 made it steep. This number, I said that you can, whatever that number is going to determine how steep your slope is, or your
What
graph
happens
is.
if it's 7 squared? Like, what is that? Is that going to change the graph?
Well, so it would be 7 times 7 is 49, so it would be at 249 would be your point.
Oh.
Okay? If you went to 3, it would go higher. That's why it keeps going up high, high, high. As your x gets higher and higher,
it?
your graph keeps going up exponentially. Okay? So, but what point is always the same? What point is always the same? Well,
7, 0.
when x is 0, what?
1.
So it's always going to go through that point 0, 1. Unless you added like 7x plus 2, then you could shift it horizontally or vertically up and down. But that's always going to be there unless you have something like that. So remember, e is just a number. Okay? So this is where a lot of people get confused because they think e is a variable. E is a number. Okay? It's just an irrational number, just like pi is a number. Okay? So the exponential function f of x is of e to the x. So it's just a number.
But what does that mean?
It means that if e is 1, you're going to go through the point 1, 1. I don't have a graph out. Well, then if E is 2, then what? It's E squared, which would be this whole number squared. You could do that on your calculator, by the way. Pull out your calculator so that you know how to do these. And if you hit the, your calculator has an E button. So it's right under the, sort of about the parentheses button. Then you can fill it in. So if you put in E squared, it would give you a number, mine estimates it's a 7.38906. So 2 would be somewhere like 7, 8.
Wait, then why is yours up there 2 points?
Where?
Up there 8 points.
That's E. I said E squared. If you put in E2, if I go to 2, okay. E to 1 would be like 2 point whatever.
Yeah.
Then 3. So we just keep going up exponentially and get infinitely small or exponentially small
Wait,
as you
so
go to
that's
the left.
like our y equals x squared. That's like our, like when we were relating graphs, that's like our y equals x or y equals x squared. Correct.
Well, y equals x squared is going to be a parabola.
Yeah.
So
But
this
like
isn't
when we were
parabolas.
doing parabolas in quadratic, is that like what we did? It's like our model of the simplest one, or?
Well, eventually we'll model. We're not modeling right now. This isn't modeling.
Okay.
This is just showing you what it looks like.
I don't
So the
know.
graphs are going to look like this. Okay?
Yeah, that's what I mean. Like the simple one.
Right, this is a basic exponential function, looks like this.
Yeah.
Okay? Alright, so
I know what I'm talking about.
outstanding.
What did I say, sarcasm?
Formulas for compound interest. So when we apply this idea, first came up when we compound interest, or when we calculate compounding interest. And you need to memorize these two formulas. And I need to break down, because I went over there and I didn't. This is, So after 10 years, the balance A in an account with principal P and annual interest rate R in decimal form is given by the following formulas. So, let me go grab my dry erase marker. Those are R and N. They didn't type well out as a fraction. So you probably remember this from beginning of high school, this calculation of interest rate. And you have that the amount in an account is principal, 1 plus R. And then as you compound your interest, you could decide, for example, if a bank compounded it once a year, you would just have 1 for your N. Now, N is always your number of times it gets compounded. So if you compounded it once a year, it would be 1. If you compounded interest quarterly, it would be a 4 for your N, because 4 times a year. If you compounded it weekly, it would be 52 for your N. Okay? So the idea is, with this E, is that if you continuously compound, if you're constantly compounding, if you never stop, that's where you get this formula for the continuous compounding. Amount equals principal times E to the rate times T. And your T is the number of years. Okay, so if you let the number of compoundings increase without bounds, the process reaches what is called continuous compounding. And so those two formulas are really important. So that's what you're going to use for most of this section here. Okay, so you need to know whether you're continuously compounding, or if there's an N, that means there's a set number of times. So if I was compounding once a year, my N's would be 1. Okay, and I think that is all there is in this section. But we're going to do some examples. What are you confused about?
Where was it? Did they give that to me? Hold on, let me have it. Yeah, what do they mean by continuous?
never stop compounding. There's not a certain number of times they're gonna compound it each year, they're gonna all keep compounding it, not stop.
But what does that mean? Like number?
It means that the n disappears when we use e. That's what the whole point of the e was. Compounding. So let's do some examples, and let me shut this off.